presentation of this afternoon, which is Susan Brantley's presentation. Susan, of course, is the Wollaston medalist, the senior medal that the Society awards. And so I'll hand over to Susan, who can make her presentation, and then there we are, everything we need.
Thank you. So I've never done a talk after tea, so that's perfect. I even made my daughter have tea for the first time in her life. So I thought I would talk about the critical zone science initiative that's happening in the States, because to me it's one of the most exciting new initiatives that really allows us to be true geologists in the same frame as the geology of yesteryear, where you try to bring every aspect of the environment together. So the critical zone was coined to be a phrase that connotes everything from the upper canopy down to, maybe the bottom of groundwater. That's, imprecise, but it includes really all aspects that we really need as a species. And I like, if we could dim it a little bit. I think that's my friend Kevin up there. Well, when you come here late and give your slides late, you get to meet him personally. I kind of like this slide because I like thinking about the Earth this way, and in terms of there's a physical structure to it, and it has a beauty. And then there's sort of what I think of as the chemistry, which puts in all the colors and the flavors and everything, and really trying to put those things together. And then, of course, there's the biology that's sort of working across that we really have to understand as well. And so this is like a theme in my talk, trying to think about the physical structure and the chemical structure, and then sort of how biota catalyze it. And if you feel at the end of the talk that you don't understand it all, it's because I don't understand it either. This is really a jigsaw puzzle that we're putting together, all of us, and I'm just going to give you some snippets of kind of what we're thinking about. I'm going to focus on shale, and it's interesting to me that most geologists, we like to go to mountains, we like to go to the granites and the crystalline rocks. Shale doesn't make beautiful, peaks and that sort of thing. It's sort of the non-charismatic weathering lithology, but it does form something like 25% of the surface of the Earth. It's very important. It is very charismatic if you're interested in drilling, however. So in the beginning of the talk, I'm going to be talking about weathering and the surface. At the end of the talk, I'm going to end up with some of what I've been working on, just some thoughts about water quality and the shale gas revolution. So water quality and what people call fracking, so high volume, high pressure fracking. This scrolls through, I live in Pennsylvania right here, but this goes into Ohio and West Virginia. So from 2004, these are the number of shale gas wells that were drilled. So in 2004, it was the first one using this high volume fracking. We have like 10,000 wells that have been drilled. And that speed, that explosion of drilling, especially in Pennsylvania, there were some water quality issues, which I'll talk a little bit about. The public got excited about it, good and bad, and that created pushback around the world. And so I think that's kind of interesting to think about as well. So let's start with the weathering. We work in a small watershed, like very, very tiny watershed outside of Penn State, so in the center of Pennsylvania. It's all on the Rose Hill Shale. And I should have put an image where we have all the instrumentation in here, because we work with hydrologists, ecologists, geophysicists, soil scientists, and we have wells, we have lysimeters, piezometers, are really trying to understand, why is the geomorphology the way it is? Why is the chemistry of the soil the way it is? Why is the biology the way it is? And really putting all that together. So this is the way I think about the system, and this is sort of the world view for the talk, because mostly I'm going to talk about regolith and soil and how it forms. And let's pretend we're at a ridge top, so an upland system. And basically what's happening is we have bedrock down here at some depth, and we have water that's meteoric water that's moving down. It's oxygen and CO2 charged. So it's in equilibrium with the atmosphere, and then these rocks, they are equilibrated at some deeper depth, pressure, and temperature. So the soluble minerals dissolve, concentrations increase downward, And then we can talk about this interface here as advancing into the rock, and that would be the weathering advance. Well, one of the good things about working at a critical zone observatory, which is what we call a system like this, one of these funded initiatives in the United States, is we have many people measuring different things. So we measured the rate that this advances, this weathering advance with uranium disequilibrium. It looks like it's advancing at something like 40 meters per million years. Well, now imagine you're standing at that ridge top, and you're going to stand there for a geological amount of time. So this is, water flow sort of at our time scale, but now we're going to stand up here and get really old, okay? And it's going to be eroding here. And if we maintain regolith for any amount of time, which must be true because it gets weathered and that takes time, then as the material is eroded at the surface, this material down here is changing into rock fragments and then changing into soil, and those particles are moving up and out of the system. And to me, this is the coolest part of, can we understand this? Can we model it? Can we quantify it? And can we then say that we truly understand this? That's really what we're all trying to do. So water increasing in concentration down, rock fragments coming up, typically getting smaller as they come up. We can also measure the rate of erosion. It's like 30 meters per million years. And if this was in steady state, where this was advancing at the same rate that this was eroding, then this thickness would stay the same over time. And we often work as if steady state is occurring. We don't actually know that it's occurring. And in fact, probably most systems are out of steady state and they get perturbed, but I think they're always moving back to steady state. I think there's always feedbacks that pull them back to steady state. All right, so what I want to do is just I'm going to go a little faster now because I tend to go too slow. I'm going to try to, talk first about thinking about the system as it comes up from below. And think of this as the cathedral windows as it's coming up from below. What's happening to it structurally? Well, shale is a sedimentary rock, so there's bedding planes. And what we see in our system is, if you drill down to 15 meters depth, you have a very low fracture spacing. This is from 0 to 35 fractures per meter. So you have a low fracture spacing. And then as you come up within about 8 meters, you start to get these much higher fracture densities. So the rock, as it's moving up, is responding to the surface and opening up, and that's allowing the water to get in. I don't have an outcrop picture from our watershed because there are no outcrops. This is actually, my daughter could tell you where this is from. It's from up on Lake Erie. It's a different shale, but you can see what I think this probably looks like if we could have it in an outcrop. You can see how the fracture density is higher up here. Maybe this is a little higher than we've got over here. That's kind of the picture you can have in your head. Well, why is this? Well, we think it's because, and Nikki West has made some calculations to calculate that it's related to the fact that we're about 75 kilometers south of the greatest glacial advance of the last glacial maximum. So here's the little watershed. This is a LiDAR image. It's a relief, it's contoured for relief. And basically what we think these fractures are from is from frost wedging. So water getting down in and then freezing and causing fracturing to open up. Well, that's the data that I showed was from boreholes, and that just gives you an image in one place. And of course, you can go and do geophysics. And so Nikki West has also done geophysics with my husband Andy Nyblade, Eric Kirby, a geomorphologist. So now we're kind of looking at this in a cross-section. So this is ridge to valley, ridge to valley. This is the sunny side, so south-facing, and then the shady side. And so the blue color, essentially like 2 kilometers per second, is good shale. And then some of my geophysicist friends call this damaged shale up here. It's not damaged, it's weathered, which is what I study and I love. So as you change color, you're going through sort of the fractured shale, highly fractured shale, up into the true, what we would call soil, because you can auger through it and get it out. And you can see that it's thicker over here. So we see this in several watersheds, all in echelon. And so this is the pattern that Nikki has been making a quantitative model for, showing that you can't produce this kind of fracturing from frost wedging today, that it has to be related to the fact that we were in paraglacial conditions 15, 20,000 years ago. Well, it turns out if you look at the geophysics data and plot it versus depth, So this is the P wave profile, so the velocity of the P wave from that refraction seismic, and this is depth into the subsurface. You can see that, down here, this is the pristine bedrock, and then you start to get slower bedrock as it's fracturing, and this is where the depth of the major fractures are. Well, we can plot our geochemistry on top of that. This is for potassium and this is for magnesium. In looking at weathering, we like to plot what's called tau, and it's not really important exactly what it is, but it's a way of looking at how much of an element has been removed from the rock. So if you're at parent rock being the unweathered material, your tau value would be about 0 here. And so these data points show you sort of the jumping around. It's a sedimentary rock, so it's not, every layer isn't constant. And then you're starting to lose your potassium up here when these fractures come in. So as that water goes in, you're thinking of that first picture, and the water is taking out the potassium. So this is weathering pretty much of illite, which is in the rock. And then this is magnesium, pretty much the same thing. A lot of variability, of course, but then you get heavily weathered at the surface. So now let's think about this a little bit deeper. Again, we're bringing the rock up into a system. Well, here's from 0 to 30 meters. This is now the water table on here. Here's the sort of deepest water table we've ever observed. This is a little bit shallower water table. And this is sulfur, weight percent sulfur. And every shale has a little bit of pyrite in it, which is fool's gold. And this particular shale is not a black shale, so it's pyrite poor. But every time we look at a borehole, we see pyrite, and then we see, this is what I call a reaction front. This is where the pyrite gets oxidized and removed. And then you have very little pyrite up here. So pyrite, oxidation front. And then you typically are close, at least up on the ridge tops, they're close to where the water table is. So this is a picture of what I think you should think about in the subsurface. This is the top of the ridge, so it would be up here or up here. And then here's the summer water table and the winter water table. This is down in the valley, and I haven't showed you a borehole down in the valley. Here's this upper zone of fractures that I've showed you some data for in a picture from a different shale. And then between the winter and summer water tables, here's that pyrite oxidation front. And now if we look over in the valley floor, the pyrite oxidation front actually goes deeper here, and it goes a little bit deeper than this highly fractured zone. And so what I think this is pyrite oxidation, as I've already mentioned. This is also mediated by bacteria because both iron oxidation and sulfur oxidation are all catalyzed by bacteria. We would love to get someone working with us on that problem. There's also a reaction front on here with carbonate. We see very little carbonate, very little calcite up here and here, and then beneath this we start to see calcite. So I think these are reaction fronts that are, in essence, like moving into the subsurface that more or less have the topography of the landform. Well, we also wanted to not only think about fracturing, but also to think about as these rock fragments move up through the system, are they staying the same? I can pick up these rock fragments from my borehole or from my soil, and they look like a rock. They just, but are they the same? We wanted to measure the very, very tiny pores in these rocks. So we went to a nuclear reactor, which is manned by NIST, in order to make a neutron beam that you can put rock samples in, and then the neutrons scatter, and you can measure the porosity. So we did this just south of Penn State. So here's the rock fragments, the shale fragments. Neutron beam comes in, scatters. It actually makes a target. You can see the scattering. And looking at the intensity as a function of the scattering, you can then back calculate what the pore grain interface is in the rock and get the porosity. So we did that, and this is what it looks like. So here's the particles that are coming up. Look at the dark circles, the dark symbols. There's a very low porosity, pretty constant here, but that's the water inaccessible porosity, so the pores that the water can't get into. And then there's always a little bit of porosity that water can get into, connected to the water. So it's higher. This is the total porosity. The difference between these two is the water connected. And what you see is when you hit this oxidation front, all of a sudden your rocks start to have slightly more porosity. And these will look just like rocks. You wouldn't know this was happening. These are pores between nanometer and 10 microns or 20 microns in size. And you can see it happening up here as well. And then likewise, I feel like you're going to fall into your lap, David. That would be exciting. So here's another tau plot. Here's that parent composition. This is magnesium. So no change from the bedrock. Then you're losing magnesium above this oxidation front, and no loss of potassium particularly. And then these are just two different boreholes. I may have forgotten to tell you this. This is on the north side, and this is on the south side. And then you don't lose potassium up until very, very, very shallow. And so again, you're sort of seeing those two things going on. The rocks coming up, opening up, and then also changing in chemistry. So this is really the same thing. This is the porosity. We have a little bit more data up here. Look at the scale break. This goes down 20 meters and then a scale break. This is where you can auger through it. So the porosity, this is the unaltered, and then in that sort of 5 meter zone, you get a little bit of a porosity jump, and then your porosity starts going up all the way. So you can really think of this as not only are these fractures opening up and the rock fragments getting smaller, but the pores are actually growing inside the rock as well, and that's how the whole thing is weathering. So you can also look at this as a rock fragment size. This actually, again, we don't have outcrops where I am. This is from Flynn-Limon, which is up in Wales. So just to give you this idea, we're looking at the particle size that's coming up and moving up through the soil. So it comes out of the part that we can't auger through at about 5 centimeters, these sort of blades of rock, and then it quickly breaks down to sort of tens of centimeters and gets smaller as it gets weathered. So that's kind of the rocks coming up part of the story. Let's do the water going down. This is what the two of the three most important reactants in the weathering system. It's water, CO2, and O2 is what I would say. And the water and CO2 come down from the atmosphere, and then the CO2 is pumped in from plant life, from microorganisms, and this is where the dissolution occurs, and then water goes, infiltrates down into the groundwater. So we've got all sorts of data of soil CO2 that we're starting to try to put together into models. This is depth from the surface down to 1 meter, and this is coming down ridgetop, mid-slope valley, ridgetop, mid-slope valley, and this is partial pressure of CO2. So you really can see the ridgetop, of course, is drier. The water comes in and infiltrates out pretty quickly. Down in the valley, the water comes in and it's held in the soil longer, so the soil moisture is higher for longer. And these are just contours to show you how much soil moisture is there. Well, if there's moisture and if there's organic matter, which there is in these soils, then you're going to have respiration and production of CO2. And so you can see that this is where you're producing CO2, so you're making the acid that is dissolving the system. So we've been trying to make models of this. I think that the state of the art right now is we can make geochemical models that calculate the speed of weathering. We can make fracturing models that make fracturing. What we really can't do, but everyone's kind of working towards, is to pull those two things together where you have fracturing and weathering occurring together. But here's a geochemical model. This was done with Yves Goderis from France. This is depth again down to 0.6 meters, I think that says. And now this is time, so it's a slightly different plot than what I've been showing you. And it's contoured for the rate of weathering of the magnesium clay, magnesium iron-containing clay in the rock. This is the sun-facing side, and this is the shaded side. So this is the time over 1 year. And so this is our calculation of how weathering is occurring over time. Darker colors, higher dissolution rates. So what we see, and this matches the data that we see in the aqueous chemistry from the system, is that on the sun-facing side, the dissolution rate is faster than on the shaded side, the south side of the watershed. And so we can actually predict this kind of thing. And what we're working towards also is being able to predict that forward in time as well. Well, that's interesting in that I've told you, I showed you this before. This is the seismic from this is the sun-facing side, and this is the shaded side. You can see that the regolith is thicker over here. Turns out that this whole side of the watershed is steeper, And there's 3 en echelon watersheds. They're all in a row, all on the Rose Hill Shale, and they all show that. And so one of the ways we think about this is that it turns out that the regolith flux out of this watershed on this side is the same as the regolith flux out of that side. But what they call the erosional efficiency on this side, so sort of like the ease at which the material can move, is higher on this side than that side. And so in order to get the material out at the same rate, if you will, this side has to be steeper. And so this side is steeper because it has a lower erosional efficiency than this side. And why is that? Well, we think it's because the wetting and drying on this side, it's the sunny side of the catchment, continuously breaking up the rocks, allowing the material to move out. This side, it's shadier. If you're a skier, this is the side you'd want to ski. This is where the snow stays longer. And so material just doesn't get moved out of the system as far. And so this is retaining material on this side. And as a matter of fact, if you think now on the other time scale, sort of the geology time scale, as you move material up through this system, the fracturing goes deeper because it's on the northern or the shady side. And so the fracturing goes deeper, the water gets down there, but the material, the water, there's actually more water goes through this side. And so in effect, the two sides are very different. The physical weathering is deeper. This side gets more, the extent of weathering gets higher. And then it's also steeper because its erosional efficiency is lower. So now just to kind of finish the story and work my way out to the end where I wanted to bring you back to fracking and to sort of think about it from a water resources point of view. I just wanted to point out that we're also thinking about what's controlling the incision of the watershed, so the creek as it cuts down in at the center of the watershed in the catchment outlet. This is that picture I showed you before. I just want to remind you of this fractured layer. What we think is happening is sort of a standard idea would be above the water table, water would be moving only vertically. Actually, what we think is happening is because this is so fractured and the fractures are horizontal, that the water is actually moving mostly downslope. Only some of it makes it down this far. And that if you look at well water down here, what we see is in the summer, early fall, we have high dissolved oxygen in the well water here, and then in the winter it swings back over here. And so we kind of get this movement between the two, which has to do with, is it getting oxygenated water from the hill slopes, or is it getting water that's kind of moving this way that is oxygen depleted? And what we actually think that is possibly happening here is that this oxidation down here may be the advance of the incision. So we tend to think of incision as being a mechanical process that incises down into a rock, but we think that it's possible that incision here may be this pyrite oxidation that's related to this oscillation here and bringing the oxygen down and oxidizing at the bottom of the watershed. So now this is just to kind of walk me back out to the sort of fracking story. This is a classic picture from Toth of these sort of deep water flows. And we've been talking, so here's the land surface, and this is what water does. These are sort of topographic water flow lines. And we've been talking about a little watershed up in here where we've got little water flow lines coming in. Well, the whole controversy, the public controversy around high pressure fracking is really all about, I'm going to drink water up here, and then if I'm going to drill down here, is the water that goes down, is it going to come back up? Is it going to bring back up some of those fracking compounds? That has been one of the things that the public has been most worried about. And of course, so my point is that the study of the critical zone is really, it's very pertinent to what humans are interested in, what the public in Pennsylvania and over here are interested in, namely, can we understand these flow lines and can we make quantitative predictions? And the reality is we can't. We don't really know how to model these very deep flow lines. We have models to do it, but we can't necessarily understand everything there is to know about it. So we need to study them in order to understand what might or might not happen. Now in Pennsylvania, if you go some 500 feet into the subsurface, you're mostly in fresh water. And then below about 500 feet, you start to get into brackish water and very salt-rich water. And so just by looking at the chemistry and understanding, you can see that, you know, the flow lines, you could almost say that the brine in the subsurface is where you're not, you know, bringing down the meteoric water and pushing it back up. And so you can actually see from data, not just from models, that the likelihood of water, high pressure fracking water pumped down thousands and thousands of feet in the subsurface into the shale, the likelihood that that would come back up is extremely small. And as a matter of fact, I've been looking at all the data from Pennsylvania and our area. There are no incidents where high pressure fluids that were pumped into the subsurface, into the shale, have come back up to the surface. There's none in Pennsylvania where we're fracking at, you know, 7,000 feet in the subsurface. This is the shale gas rig in not too far from where I live. But there are problems, and that's what you've heard about. I think that the number of problems is actually pretty small compared to the number of shale gas wells, but there are problems, and I think that we need geologists working on these kinds of problems as well. Up in the northern part of the state, up in Bradford County, I told you there was almost 10,000 wells. This is one of the counties with the most high density of wells. So here's 4 miles here, and they like to drill these wells on the ridge tops, and each of these red stars is a well. And we were working with a consultant who worked on a problem where all these active gas wells and some homeowners got methane coming up in their well and started to have some problems. So we went there, and here are the gas wells that turned out to be problematic. Here are the homeowners' wells, which were in a valley on Paradise Road. And here's some of the wells themselves. And what we ended up discovering was that there was methane there, and they were able to pump down a lot of cement into these wells in order to stop the methane. But there was also a very small amount of 2-butoxyethanol in the water. And it was at such low concentrations that the regulator was unable to identify it, and so we were able to identify it with the help of Frank Dorman at Penn State, who's an analytical chemist. The gas company denied that it was there, but you could see it in the water. It comes out and it looks like a foam. You can see this looks like almost dishwasher foam or whatever. And they told me that that wasn't happening, but I'll tell you it was. But this was extremely rare. I want to make that very clear. I mean, this is a piece of the story, is that there are a few problems, but they're rare, especially when you look at them compared to the number of shale gas wells. This is the geology of that story. Here are those wells. I just showed it to you in plan view. Here's the homeowners' wells. This is the fault that outcrops on the surface. Here's the actual wells projected on this block diagram. This fault looks like this. They were drilling down here to the Marcellus. This is at 2,000 meter. Turns out all over northern Pennsylvania there are gas shows in the younger rocks, and so there was lots of problems with gas getting out. As I said, they were able to solve that by pumping cement down in here, but it turns out that there was some way that this 2-BE, this 2-butoxyethanol, moved in the water from one of these wells. We don't really know which one. Presumably it moved along the fault. So it moved along in this direction on this fault, and then it moved, up dip along the bedding to get from one of these wells over to here. And you can read the different ideas that we had for how that could have happened. 2-BE is used in air foam, which is a compound that they were using for drilling in one of the. Actually, they never admitted they were using it. I don't know whether they were using it, but a lot of the companies were using it. So this type of problem was very rare in Pennsylvania. It did happen. I think it happened in other places too. What was brilliant about this was that the homeowners litigated, and then when they won their case, they insisted that all the data go public. So you can read our paper, and all the data is there. And this is obviously what we need more of so we can understand these problems. The more common problem, this was one of the only cases that's been published like this. The more common problem is methane contamination in groundwater, but even this is quite rare also. So the Pennsylvania Department of Environmental Protection said there were 55 cases, verified cases, methane getting into people's groundwater due to oil and gas activity from '87 to 2013. That actually precedes the high volume fracking. So, you know, it's a little bit, it's a bigger number than it did than would be associated with the fracking. And this was at the same time that about 7,000 wells were drilled. So really the rate of problems is really small. And I think it's really important for geologists to get that story out. However, 38% of those 55, the Pennsylvania DEP, actually attributed them to old oil and gas wells. Pennsylvania was the site of the very first oil and gas well drilled, 1859, first commercial well drilled, which was like right up in here somewhere. We have something like 350,000 oil and gas wells, and about 100,000 of them we don't even know where they are. And I'm sure you've got some of that kind of situation over here. And even sometimes when the companies knew where they were, or they thought they did, they would drill and have issues. So this was a well that was drilled by one of the majors and someone that, you know, a company that was doing everything they could to figure out how to avoid an old well that had been drilled in '32. And somehow there was connection between the fracking, which is laterally, and this old well somehow, and methane shot up in a different location. And this is methane coming up with water in a nearby location. And this was called a methane geyser in the press. And it's this kind of thing that gave the activity a bad name, but again, the rate of it compared to the number of gas wells is really quite small. Mary Kang and Michael Celia have been trying to estimate, you know, how much methane we might be losing. Many of these old and abandoned wells are leaking methane all the time. And the Pennsylvania DEP is trying to plug them when they're problems. But if it's just happily leaking and not making a problem, they're just letting the methane go. And I think this is something that we have to think about too. They estimate that 5 to 10% of anthropogenic methane emissions in Pennsylvania could be from some of these legacy wells. So that's my talk. Thank you. I just tried to show you that as rock material moves up to the surface, it re-equilibrates both by fracturing and chemistry. And I think it's really a cool puzzle to work on how we can quantify that and put it into models. I think the information from the surface is carried down quite deep, kilometers in terms of pressure, and then the water chemistry going down into depth. And that kind of defines the base of the critical zone. And the base of the critical zone is what people want to know. They want to make sure that their water isn't going to be contaminated. Throughout, biota catalyze this process, the CO2, the pyrite oxidation. And at the same time, the biota also, I think, stabilize where there is a gradient that the biota can live off of. They try to stabilize it so that they can live there for, you know, as long as possible. And then we're extracting resources from depths that's actually changing the fluxes of gases and letting gas from the subsurface leak out, and of course burning hydrocarbons. And I think we need to be able to predict these processes and understand them and put them into quantitative models, and that's what many of us are trying to do. So thank you very much.
Thank you. Susan is prepared to take a couple of questions. If there are questions, I'm conscious though that we are up against time, and there's time to talk over a glass of wine in the library as well. If anyone has a burning question, if you'll excuse me saying so, Peter.
Can you tell isotopically whether or not the methane in the wells is from coal-measured rocks or actually from deeper shales?
There's been a huge amount of work done on isotopically looking at the methane. And in this part where we were, I don't think coal measures was the problem, but you know, the isotopes can tell you a lot. Fred Baldessere has worked on that a huge amount. What he'll tell you is you can't fingerprint it, but you can eliminate a lot of possibilities, and you can often, when you put it together with hydrologic study and geologic study and a history of when things happened, you can get pretty close to understanding what's happening. But you know, the isotopes are not a perfect piece of the story. If you look at the methane and the ethane isotopes, that helps even more.
Thank you. Please, Tom.
So I have a question about the steady state business. If you perturb a system like that, you reduce the rainfall, you increase the erosion rate. What's the return time to the new steady state? How resilient are these systems?
I think that's a great question. I don't think we really know the answer to it. One of our papers we published that the return time at Shale Hills was on the order of 100,000 years. It was long. It might have been longer than that, but that kind of order. And so the climate changes would be faster than that, and so it would always be lagging. And so the way I think about these is that in systems where you are maintaining regolith, I think that you may always be being perturbed away, but always trying to move back to the steady state. And I think there's a lot of feedbacks in there that pulls it back. But that's a very good question. It's something that a lot of people are trying to model and be able to answer.
Question here, please.
Do you have any subsurface mapping, seismic or whatever? Because the geological model you had linking the wells to the well that was following was pretty simple.
So, okay, so you're asking about the fracking story right at the end.
No, I'm asking you about the geological cross-section you had.
So are you talking about the fracking story or the beginning with the weathering story?
No, you had a cross-section with just one fault on it.
With the 5 wells projected.
Right, so it's the fracking story. That's what I thought. Right, okay. There was a lot of seismic done, and most of the companies have huge amounts of seismic. They were all, I don't know if it was all, but a lot of it was put into litigation, and so some of that data has been available, and that model that we made was based on everything that we understood from, what was released publicly from the companies and that sort of thing. But there is a lot of seismic work that's been done up there for sure.
Did you actually get the opportunity to do it yourself?
Did I? No. No.
Okay, one last question, I think, please, if that's okay.
Worry about the use in monitoring methane to find faults that don't show unconventional means. In that part of the world, there are lots of faults that have no surface expression, and yet obviously there might well be leaking methane. Is that showing up at all?
So I think so the question is, can you use methane to find faults? So one thing I didn't say, and I should have said, is that in this part of Pennsylvania and lots of places around the world, methane is released, it emits naturally all the time. Some of that methane is biogenic, so it's produced by bacteria. Some of it's thermogenic, so it's produced at depth and it's coming up naturally. It's very difficult to get data. This is one of the problems, one of the things I've been working on is releasing data as much as possible. And we've gotten a lot of data for very small parts of Bradford County, not exactly in this part where I'm talking about, but because it's hard to get data there because the companies are not releasing it, as a matter of fact. And we started, where we've got a lot of water chemistry data, we started mapping it, and yes, indeed, the methane maps the fractures. And it tends, lowlands, just like in this London story that we heard, the lowlands tend to be fractures. So the methane that's coming up tends to be along lowlands as well. And so I think you could use methane to map fractures if you want. We've also come down streams and measured methane in streams, and you'll see places where you cross a fracture where there'll be high methane coming in. We did that in 15 streams in Pennsylvania, and lo and behold, one of them, there was a big amount of methane coming in at one point. And we looked at all the isotopes. It all looked like thermogenic. It looked like Marcellus. There's a way you can actually see if it looks like Marcellus. It doesn't prove it, but it looks like Marcellus. And it turns out that there was a leaking shale gas well not that far from there that we didn't even know anything about. So that's one thing we're following, because I think looking at methane in streams will be one way to try to find problems, whether it's an old legacy well or one of these new shale gas wells.
Thank you very much, Susan. I'd just like to join you. Thank you, Susan, again.
Thank you.